Hello everyone, it's Benny, and welcome back to the Occlusion Culling tutorial series. Last time, we talked about the theory of so-called masked software occlusion culling, and we saw, in theory, it should meet all the criterion to be an awesome, near Holy Grail-esque version of occlusion culling. But what is it like in practice? Does it really perform as well as it seems like it might in theory? That is the topic of this video. Let's get to it. Something you have to be careful about whenever you're dealing with an academic technique like this is, well, it's academic. It has not yet proven itself in the fields of battle. The biggest resource we have is the original paper, which claims it can do this. But obviously, that's biased because, well, the paper's done by the authors who obviously want to show their technique is awesome. And it's also biased because this particular paper is by Intel, the people who make these really awesomely wide simmed units that this technique takes advantage of. So, does it actually do as well as they claim in practice? It's worth checking into that, because it's not uncommon for papers to exaggerate the effectiveness of their techniques. So let's see what the paper claims. The paper claims that for a scene of 73 million triangles, and with an occlusion mesh of 143,000 triangles, they can do occlusion in just about 5 milliseconds in the worst case, and giving a worst case render time of about 10 milliseconds. That's what they claim. And to be clear, I believe they state their hardware somewhere. Yes, they claim to be running this test on an i7-4770 and a GeForce 760 GTX. So, that begs the question, how does this run on anything that isn't that hardware? Especially an AMD processor. Well, that's what we're going to put to the test. So the first thing we need to know how much faster their i7 is compared to, well, my processor. And that's always a hard thing to determine. It's always hard to really get a general idea of, oh, this CPU is going to be X amount faster than this other CPU on this piece of code. That's not an easy thing to do. In absence of actually having the hardware to test it, I can get a rough approximation, which is really all I need. I need just a rough approximation by comparing some CPU benchmarks. So, according to Passmark, the single thread rating for the i7 is 2254, which means nothing in particular. It's just an arbitrary benchmark number. And the arbitrary benchmark number for my processor is 1602. That's what matters. We can expect the i7 to be somewhere on the order of 40% faster for a single thread. And single thread is what matters because they're claiming to do all this processing on one thread. No I just bumped the microphone. No multi-threading at all, just a single thread. So that's the first thing. Another thing, we're going to want to further adjust the i7 figure because this processor supports 256-bit simmed vectors. And this processor only supports 128-bit simmed vectors. So yeah, this doesn't even have the fancy vectorization technology that Intel wrote the paper around. This is just using the typical 128-bit vectors that have been around pretty much forever. So we can add basically an extra factor of 2. We can expect roughly a factor of 2 times performance increase from having bigger vectors for Intel. Approximately. So our factor is somewhere around 2.8 times faster on the Intel. That's roughly what we can expect. Now, the other thing is, our 143,000 triangle mesh, they're not going to be rendering every single one of those triangles every single frame. First of all, some of them are going to be eliminated just by being outside the view, and some more of them are going to be eliminated because you can do hierarchical occlusion culling with this. You can say have your scene in an OCK tree and say, oh, this node of the tree is not visible, so I don't even need to bother doing occlusion checks for anything further here because I just all that isn't visible. And that can save a lot of both GPU rendering and occlusion coloring rendering. So it's difficult to know exactly how much of this, is going to be in reality. We know it's going to be less than 143,000. We know it's going to be more than 0. But we can just give a rough ballpark estimate of somewhere between 3 to 5 times. So I'll take the geometric mean of that. So square root of 3 times 5, and that'll be my factor. So 143,000. Honestly, 2 is reasonable. So I'm going to say square root of 2 times 5. So there, 143,000. Alright, I'll split the difference by my original estimate. 2.5 times 5. There we go. It's an estimate. I'm not going to worry too much about it. But yeah. So, why did I just divide? Right. So we can expect somewhere on the order of 40,000 triangles per second. It might be a whole lot more or less, but this is a general ballpark figure. And they claim to do this once every 5 milliseconds. So I'm going to divide by 0.05 to get the number of triangles per second. So somewhere on the order of 8 million triangles per second will be the equivalent of what they're claiming. But that's on the i7. We still haven't adjusted for what it would be on the Athlon X4. So given the performance factor, we should expect somewhere around 2.8 million triangles per second if the performance is what they're claiming it to be. Because that's what we can expect from the difference in processor, about 2.8 million. So, what do we actually get? Well, if you look at our masked occlusion culling for single-threaded, it is somewhere between 6.86 million triangles per second and 0.09 million triangles per second, which might seem a little bit weird, but this is using the official Intel test tool, the one they provide with the paper and all the code they have with it. And unfortunately, it doesn't work precisely with the example scenes, or this comparison will be a lot easier. Instead, they opt to generate a field of random triangles of a fixed size and test, the rated triangles per second. So for a field of random 10 by 10 triangles, and by the way, this is all 1080p rendering. So rendering a random field of 10 by 10 triangles in 1080p using this technique, my CPU can do just under 7 million triangles per second. If it's 500 by 500 triangles, it goes way down because so much is spent on fill rate. In practice, though, you can expect probably somewhere between 75 by 75 and 25 by 25 to be about the average number of triangles per second in a realistic game scene, because that's really how it works out. Usually you have a few big triangles and a good number of tiny triangles and a good number in the middle, so somewhere in the middle is probably somewhere realistic. So we should expect somewhere between 3.71 and 1.31 million triangles per second on my machine. And lo and behold, that really lines up well with the performance figure they're claiming on the i7 adjusted for the CPU speed. So, moral of this whole convoluted story, the performance figures actually seem to be relatively decently done. They seem to be decently lined up with real world, and they seem to apply well even to processors that aren't by Intel, even processors that don't have the fancy SIMD technology they're promoting. It seems to be a good general result. So, now that we know that this technique seems to do just about as well as they claim, even on non-Intel hardware, even not using Intel's big, fancy SIMD technology, the question then comes in, how is this going to work on a realistic processor in a realistic game scene? Because both of those are unrealistic. Most game scenes are not huge 73 million triangle meshes with a nice, neat 143,000 triangle occlusion mesh. That's ridiculous in just about every sense. Most games are not going to be like that. And also, they're testing this on an i7. Most people probably don't have an i7. Most people probably have, a more low-end, more common CPU. Probably something performing closer to my Athlon than an i7. Which begs the question, again, how would this perform in a realistic game scene on a realistic processor? Well, fortunately, they did a test that's excellent for this. They tested this on a Minecraft scene, which is perfect. Why? Well, if you know anything about Minecraft, it renders lots of really tiny squares all over the place. That is perfect for this because it's high geometry complexity. There's loads of those tiny squares. And because they're rendered in that voxel format, there's also lots of things covering each other up. There's lots of, well, room for occlusion, which means occlusion culling could potentially have a huge impact here. So, it has huge potential for occlusion, it has huge geometry complexity, it's an excellent representation of probably one of the worst case scenarios for this. Because you're probably not going to be dealing with that volume of geometry in reality, but, you know. So this is going to just sort of be our worst case scenario test. And in this case, the worst case scenario is a 7 million triangle mesh used for both rendering and occlusion culling. They're using a 7 million triangle mesh for occlusion. This is being software rendered, which probably sounds insane, but it's actually not as terrible as it might sound at first, because again, you can take advantage of some hierarchical benefits to, well, speed it up. Say, oh, this whole section of the mesh isn't visible, therefore I don't need to bother rendering it. And that is perfect for this technique. And also the fact that a lot of them are tiny triangles also helps because, again, the smallest triangles tend to run the fastest with this technique, so this is good. Lots of things in their favor. And indeed, in reality, for the most part, it's between about 1 to 5 milliseconds per frame on their CPU. There is this one spike, 10 milliseconds right here, but that's one spike. I can only imagine it's just an odd camera angle that performs poorly for some reason. And, well, yeah. So, really, realistically, you can expect somewhere between 1 to 5 milliseconds per frame on their setup. But what about on our more common run-of-the-mill CPU, which is a whole 2.81398 etc. times slower, give or take? Well, I went ahead and multiplied this out off-screen because, I don't know, I'm just like that. For 5 milliseconds, that would be 14 milliseconds per frame, or about 3 milliseconds per frame in the best case. 3 milliseconds per frame is more than tolerable. You can get away with 3 milliseconds per frame. That leaves you 13 milliseconds for everything else in the game. That's plenty of room. That's totally doable and reasonable. 14 milliseconds per frame, if you're targeting 30 milliseconds, 30 frames per second, if you're targeting that, then this might be okay. Maybe. You'd still have to cram everything else into 16 milliseconds per frame, but it's doable. It's more than doable. You could do this targeting 30 frames per second, but 60 frames per second, not happening. You only have 2 milliseconds left for everything else in your game logic. Probably not going to happen. But wait a minute, viewers. You might notice there's something up till now that I haven't been mentioning. An elephant in the room, if you will. Because if you remember from the very beginning, all this occlusion culling logic, all these performance figures, they're what this is like on a single core. What happens if your game is single-threaded? But what if your game is multi-threaded? We already have a technique that's very close to, if not practical, on a single core, even on consumer-level hardware. And what if we make that game multi-threaded? You see what's happening here? Yeah, if this is multi-threaded, you could just have all your occlusion culling on a single background thread, and probably still have enough room left over for a couple other things, possibly. And then, just works. You still have plenty of room left on all the other threads for the rest of your game. And there you go. You can use this as practical occlusion culling. So, in a single-threaded game, everything I said earlier still applies. You're still going to want to be very careful about the extra overhead this adds in a single-threaded game. It's not unsolvable, it's not unsurmountable for a lot of games, but you're going to have to think about it if you're going single-threaded. If you're going multi-threaded, this is almost exactly what you're looking for. It still adds overhead. It still adds a CPU overhead, which granted reduces GPU overhead, which is the whole point. But that's something to consider if you have a really, really CPU-intensive game that really needs every last cycle. This might not be the technique for you, but for just about everything else, this is going to add occlusion culling to your game. It's not going to have a whole lot of drawbacks, and it's just going to work. I'd say the one real caveat is if you're targeting extremely old CPUs, that might be an issue. Or if you're targeting mobile. If you're targeting mobile, well, you could probably still pull a few tricks to reduce the overhead. In mobile, you can probably reduce the overhead in a number of ways, really. Mostly by doing less occlusion culling and using lower resolutions. That can probably help you a whole lot. And really reducing what constitutes an occluder or occludee to only do the bare minimum amount of occlusion culling necessary, which granted undermines technique a bit, won't be as effective, but, mobile's iffy. You may be able to do it on mobile depending what you're doing, and you may not. But targeting desktop or consoles, this is probably your guy for the job. This is an awesome technique, as long as your game is multi-threaded. But with that, viewers, that will conclude the Occlusion Culling series for now. You see, viewers, there's another angle of this that we haven't talked about yet. We've been all focused on software occlusion culling, and we've shown, yeah, this can work. This can work for a huge variety of games, as long as you're willing to pay the CPU tax to do it. But as long as you can pay that, this can work. It's definitely not free. You're going to have to be careful with that, or it's going to overtax your game, but this is well within the realm of doability for a whole bunch of games. You pay the tax, you get the occlusion culling, and it'll just work for the whole game, and everything will be awesome. But there's another angle to this that we haven't discussed. Yeah, moving all the math to the CPU side is one way of avoiding the occlusion query bottleneck. The other way is moving it all to the GPU side. And for a very long time, this had a fundamental problem to it. And that was the issue of draw calls. If the GPU wanted to know about some mesh, even to test it for occlusion, that requires a draw call. And it requires a draw call for everything that must potentially be drawn, even if it's ultimately occluded. Which of course defeats the entire point. The whole point is to eliminate draw calls and not have the GPU deal with so much. But in more modern GPUs, there's a new command. The draw indirect command works just like drawing normally, but it will only actually submit the draw call if a certain condition on the GPU is met. And the logic is done GPU side, so there's no synchronization issues. So that's what it allows you to do. It allows you to submit a quote draw call without the overhead of a draw call, because the GPU will decide whether or not it needs that command. Pretty nifty, huh? It also means that potentially there's a way to do GPU only occlusion culling and have pretty much none of the issues any of the other techniques have, because GPU's blazingly fast with rasterization, so that's not going to be an issue. And if the GPU knows how to avoid the draw calls with this draw indirect command, that's not going to be an issue. So it seems like a perfect solution. So why don't we just do that? No, there's not going to be a cliffhanger, don't worry. I'm just going to tell you. As far as I know, right now, none of the techniques that try and do this perfect it. There's a lot of things that attempt it, but they all still have just a couple of meandering flaws about them that hinder their practicality. Like, some of them still require you to wait a frame before using the results in the GPU, which defeats the entire point. Why are you just not using occlusion queries then? Because the whole point of potentially doing everything GPU side is to avoid that. But no, a lot of the techniques still need to have that. Some of them require you to submit so many indirect draw calls that negates the point. If you submit so many of the draw calls, they're cheaper than regular draw calls, but they're not free, and then that defeats the point. And some of them require you to set up your scene in a very, very specific manner to take advantage of the draw indirect command in just the right way to avoid all the issues, but the way they require you to set it up isn't very practical for game development. So there's a lot of issues there that prevent me from recommending it, at least as of right now, as an occlusion culling technique. It's worth looking into, definitely, especially if you're looking for like a supplementary technique. This could probably do some supplementary occlusion culling if that's what you're looking for. Like, you already have a main occlusion culling technique, but you want just a little bit extra. Oh yeah, the GPU only techniques could probably do some of that. But in the more general sense, those techniques I don't feel are really there yet. I don't feel like they're ready for the general purpose game. For some specific games, sure. For the general game, probably not. So, will they ever be ready? Are we ever going to see a true general purpose GPU occlusion culling algorithm? I don't know. Find out next time? Maybe? We'll see. Until then, thank you. I hope you enjoyed. I hope you learned. Thank you for joining me on this wonderful journey of occlusion culling. I hope you've learned some awesome ways to cull all your scenes and not have to deal with those pesky objects behind other objects anymore. And I will see you in a special bonus video coming up next. Stay tuned.